Okay, in this video I'd like to continue to talk about some topics from chapter 12.4, specifically the concept of half-life and how we calculate it, and to do some sample problems involving integrated rate laws. So, half-life is defined as the time required for the concentration of a reactant to decrease to half of its initial value from whenever you start the reaction. The half-life is a function of the rate constant, and in some cases it's a function of the initial concentration, but not always. And the formula for calculating the half-life depends upon the order. It's different for 0, first, and second order reactions. So the question is, do you have to memorize it? No, you derive it. And here's how you do it. So, write out the integrated rate law. Substitute 1/2 the initial concentration for the concentration. T1/2 the half-life for T, and then simply algebraically rearrange to isolate T1/2. That will give you your formula for calculating the half-life. So let's do that for 0, first, and second order reactions. So I'll start with 0. Okay. I'll write out the integrated rate law. Concentration equals negative kT plus the initial concentration. In place of concentration, I will put in half the initial concentration. And in place of T, I'll put in T1/2. Oops. Okay. I will rearrange KT1/2 equals the initial concentration minus 1/2 the initial concentration, which is equal to 1/2 the initial concentration, or T1/2 the half-life is equal to the initial concentration over twice the rate constant. Okay, so we see in this case that the half-life for a zero-order reaction is directly proportional to the initial concentration, and it is inversely proportional to the rate constant. Now let's do it for a first-order reaction. I will write it out preferentially in the logarithmic form. Natural log of concentration equals negative kT plus the natural logarithm of the initial concentration. I will substitute in place of concentration half the initial concentration. And in place of T, T1/2. I will rearrange KT1/2 is equal to the natural log of the original concentration minus the natural log of half the initial concentration. But that's equal to the natural log of the initial concentration divided by the initial concentration over 2, which is simply equal to the natural log of 2. Okay? Or, rearranging now, I get that T1/2 is equal to natural log of 2 over K. Look, the half-life for a first-order reaction does not depend upon the initial concentration. It is, in fact, independent of the initial concentration. For a first-order reaction and a first-order reaction only, the half-life is constant. And that's important because sometimes seeing that the half-life doesn't change gives you direct evidence for the fact that it's a first-order reaction. We'll see examples of that later. And finally, for second order, insert page. I will write out my integrated rate law. 1 over concentration equals kT plus 1 over the initial concentration. Again, I'll do my substitution. 1 over the initial concentration over 2 equals KT1/2 plus 1 over the initial concentration. Let's make that a little bit neater. 1 over half the initial concentration is simply equal to 2 over the initial concentration. So I'll now subtract 1 over the initial concentration from each side, and I get 1 over the initial concentration equals KT1/2, or T1/2 is equal to 1 over the rate constant times the initial concentration. So we see for a second order reaction, the half-life is inversely proportional to the initial concentration. So All of this raises the question, what are you given on the AP exam? How much of this do you have to memorize and how much are you given? Well, it's kind of cryptic. They give you the integrated rate law for a first order reaction in logarithmic form, but they don't identify it as such. You need to know that's what it is. They give you the integrated rate law for a second order reaction, but again, they don't identify what it is. You need to know that that's what it is. They don't give you the integrated rate law for a zero order reaction because they presume that you understand that it is a constant rate and therefore just a linear function of concentration. You are given the half-life expression for a first order reaction. 0.693 there is the natural log of 2, and you are given these definitions. So now let's move on and do some sample problems using the integrated rate laws we learned. So a certain reaction has this form. A graph of reciprocal concentration versus time resulted in a straight line with a slope that's given there. Determine the rate law, the integrated rate law, and the value of the rate constant for this reaction. Okay, so all you need to be told is that a graph of reciprocal concentration versus time is a straight line for you to deduce that it is second order with respect to A. So I can immediately simply write the rate law. Decrease in concentration of A with respect to time is equal to K times the concentration squared. I can simply write the integrated rate law. 1 over concentration equals KT plus 1 over the initial concentration. And I can write the value of the rate constant from the slope of the line. K equals 3.60 times 10 to the negative second liters per mole per second. Okay. Now, let's see. Calculate the half-life for this reaction. All right, well, I'll go back and I'll use the equation we just deduced for the half-life of the second order reaction, which is the half-life is 1 over the rate constant times the initial concentration. So that's 1 over 3.60 times 10 to the negative second liters per mole second times the initial concentration of 2.80 times 10 to the negative third moles per liter. The information in the problem also told us what the initial concentration was. So that gives us a half-life of 9,920 seconds. That is the time that it will take for the initial concentration of 2.80 times 10 to the negative third moles per liter to decrease to half of that value. Now we ask the question, how much time is required for the concentration to decrease to even further to 7.00 times 10 to the negative fourth? Well, we know the initial concentration, we know the concentration at a specified time, we simply need to calculate what that time is. So we will take our integrated rate law and rearrange to isolate time. And doing so gives us time is equal to 1 over the rate constant times 1 over the concentration at time t minus 1 over the initial concentration. This is simply the second order integrated rate law rearranged to isolate time. So now I'll plug in my rate constant, 3.60 times 10 to the negative second liters per mole second, times 1 over the specified concentration, 7.00 times 10 to the negative fourth moles per liter, minus 1 over the initial concentration, 2.80 times 10 to the negative third moles per liter. And evaluating that on my calculator tells me that the time required for the concentration to decrease to that specified value is 29,800 seconds. Here's another problem. The decomposition of ethanol on a surface of alumina was studied at 600 Kelvin. Concentration versus time data were collected for this reaction, and a plot of concentration versus time resulted in a straight line with the slope that is specified. Once again, determine the rate law, the integrated rate law, and the rate constant. All you need to know is that a plot of concentration versus time is a straight line in order for you to deduce that it is zero order with respect to ethanol. So that allows me to write out the rate law. Decrease in concentration of ethanol with respect to time is simply equal to K, which is equal to the negative of the slope, which is 4.00 times 10 to the negative fifth mole per liter per second. Remember, zero order kinetics means the rate is constant. The integrated rate law, concentration is equal to negative KT plus the initial concentration. Okay. Let's see. The initial concentration is specified. Calculate the half-life for this reaction. So I'll use my half-life equation that we derived earlier. The half-life for zero-order reaction is the initial concentration over 2K, 0.0125 mole per liter over 2 times the rate constant 4.00 times 10 to the negative fifth mole per liter per second, or a value of 156 seconds for my half-life. How much time is required for all of the initial concentration of ethanol to decompose? In other words, what's the time that it's going to take for the concentration to drop to 0? Well, we can do this one of two ways. The harder way is to rearrange the integrated rate law to isolate time. And plug in my initial concentration, 0.0125 mole per liter, minus 0 moles per liter, over the rate constant of 4.00 times 10 to the negative fifth mole per liter per second. And that gives us a time that is equal to 312 seconds. The easier way is to recognize that the rate is constant. So if I know how long it takes for half of the initial concentration to go away, okay, how long will it take for all of it to go away? Twice that. So this is simply equal to twice the half-life, which we actually see is the case. Okay. Okay. So now it's time for a first-order reaction. It turns out that radioactive decay is always a first-order process. Okay, so phosphorus-32 decays by first-order kinetics, has a half-life of 14.3 days. How long will it take for 95% of a sample of phosphorus-32 to decay? All right, well, got a number of issues to deal with here. The first of all is I'm going to rewrite the first-order integrated rate law, not in terms of the concentration, but in terms of the number of nuclei of the isotope that remains, for which I will use n. So I'll write this as n, the number of nuclei remaining at time t, is equal to the initial number of nuclei times e to the negative kt. Okay? Now, I'm going to rearrange this to isolate time because we are asking how long will it take for 95% of it to decay. So I'll divide both sides by n naught, e to the negative kt. I'll take the natural logarithm of both sides. Natural logarithm of n over n naught equals negative kt. Or rearranging further, let's take it up here. T equals negative 1 over k times the natural log of n over n naught. Okay. Now we have the problem of what do we plug in for our initial concentrations? All we're told is that 95% of it is decayed. So if 95.0% has decayed, that means 5.0% remains, or the ratio of remaining nuclei to initial nuclei is simply 0.050. So I don't need to know those values. All I know is that the ratio is 0.050, given the fact that 95% is decayed. Okay? So now, the only thing that I don't have is the rate constant k, but I'm given the half-life, and we know that for any first-order process, the half-life is the natural logarithm of 2 over k. So if you're given the half-life, you can simply calculate the rate constant as the natural log of 2 over t1/2. So natural log of 2, or 0.693, divided by 14.3 days is equal to 0.0485. And the unit is 1 over days. Remember, for any first-order rate constant, the unit is always reciprocal time. Since the half-life was given in days, we'll calculate the rate constant in 1 over days. So now I can simply go back to my rearranged equation, which is up here, and simply plug in to calculate the time. And that gives me the time equals negative 1 over 0.0485 reciprocal days times the natural log of 0.050, or for 95% of the phosphorus 32 to decay, we'll take 61.8 days. One more problem. For the reaction X goes to form products, successive half-lives are found to be 10, 20, and 40 minutes in an experiment in which the initial concentration is 0.100 mole per liter. Calculate the concentration remaining after 80 minutes. Now, it really sounds like you're not given that much information in this problem. And in fact, you're not. Okay? What we're doing here is using the information given about the half-lives to deduce the order. You're not told whether it's 0, first, or second order, but we're going to figure it out based on the information given on the half-lives. Once we have figured out the order, then we can calculate the rate constants, and then we can calculate the remaining concentration after a specified period of time. So let me be very explicit about this. Okay? Successive half-lives means the first, second, and third. So in the first half-life, okay, meaning the concentration drops from 100% to 50%, okay, is 10.0 minutes. The second half-life, meaning the time that it takes for the concentration to drop from 50% to 25%, is 20 minutes. And the third half-life, meaning the time that it takes for the concentration to drop from 25% to 12.5%, is equal to 40 minutes. Now, given what we just learned about half-lives, can we make any deductions about the order? Well, the first one, I hope, is obvious. Because the half-life isn't constant, we can immediately deduce that it is not first order. Okay? Remember, the half-life for a first-order reaction is simply the natural log of 2 over k. It does not depend upon the concentration, so it cannot be first order. Okay? Now, the second observation we can make is that the half-life decreases as the concentration decreases. And if we go back and look at our half-life equations, we see that the only order for which the half-life was directly proportional to the concentration was second order. So that means we can conclude that it is a second-order reaction. We don't even need to consider first zero order, but you'll recall that the half-life for a zero-order reaction is inversely proportional to the concentration, and that is not the case here. Okay, so now we can write out the integrated rate law, which will be 1 over x, 1 over x equals kt plus 1 over the initial concentration of x. Okay. To find k, we will use the half-life, and let's go ahead and just use the first half-life, although any of them would work, as long as you use the initial concentration correctly. So taking the formula for the half-life of a second-order reaction, I'll rearrange to isolate the rate constant k. K equals 1 over the half-life times the initial concentration, 1 over 10.0 minutes, which was the first half-life, times the initial concentration, 0.100 mole per liter, or I get a value of k is equal to 1.00 liter per mole per minute. And it's perfectly fine to use minute as your time unit. Okay? So now we can go ahead and solve the problem, which is calculate the time required for, calculate the concentration after 80 minutes. So I'll write out the integrated rate law, and I'll plug in 1.00 liter per mole per minute for K times 80.0 minutes plus 1 over the initial concentration, which was 0.100 mole per liter. This is equal to 90.0 liters per mole as 1 over x. Therefore, the remaining concentration of x after 80 minutes is 1 over 90.0 liters per mole, or 0.0111 mole per liter as my final concentration of x. Okay, I think that's about all I want to say about integrated rate laws.